8.8, Parametric Equations. This is going to be the last section in Chapter 8. This one's going to be slightly different than the rest of the material in Chapter 8. Chapter 8 is kind of like this weird collection of seemingly unrelated concepts. It seems like, well, they had a bunch of stuff that they were supposed to fit into this book, and they didn't know how to organize it. So let's throw everything in Chapter 8. All this extra stuff, let's throw it all into Chapter 8. And it kind of flows nicely. The order in which it does, it flows nicely. But we'll see. We're looking at a different way to express curves in the Cartesian coordinate plane, or rectangular coordinates. So we're going to be working with rectangular coordinates mostly, and we're not going to go over much. There are, I don't know how many examples in this section. We're only going over the first 4 though. So I'm looking through all of this, 7, 8, and it stops at 8. Yeah. So we're just going to go over the basics on what the idea of parametric equations are, graphing with parametric equations. So the idea here, which they're used a lot in physics if you want to separate each of the dimensions from each other. So 2 dimensions and 2 dimensions only. You have an x dimension and a y dimension. There's a third one, z, and that's the world that we live in. We have 3 spatial dimensions. So in this case, if I have 2, what's useful here for parametric equations is if you know we graph curves, thinking curves as y being a function of x. So we think of y being determined by an x coordinate. So if I know the x coordinate, I know what the y coordinate is going to be by a relationship between the two, and that's the function. So it's an equation mostly that you plug in x into, and you get the y coordinate out of it. So a lot of the times we can separate the x and the y coordinates in our mind. So we have an x direction and we have a y direction, and we could think of the 2 points x comma y along a curve. And on that curve you have an x coordinate, you have a y coordinate, and we could think of the x coordinate as changing with respect to some third variable, t, and the y coordinate as another function changing with respect to the same third variable. We can call it t. A lot of the times they use t, a lot of the times they use s, maybe something else, maybe theta, but theta would be a different theta than the one that we would normally think of as an angle of a vector. Not the case. So instead, we think of x and y movements separately, and those have their own determining equations, or their own 2 functions. So now we have a function. The x coordinate's a function of some third variable, and the y coordinate's another function of some third variable. So let's see what they have here. A parametric equation. It's really a system of equations. It's a set of points, or a parametric curve, sorry. Or that might be a plane curve. Yeah, this is a plane curve. So like I was talking about earlier, we think of a curve, right? And that curve can be generated by taking an x and a y coordinates separately. So these are plane curves, sorry. So a plane curve is a set of points x and y such that x is equal to some function, x of t, and y is equal to some function, and they're using f and g instead of x and y. So f of t, so it's a function, and then g of t because we have a second function. And f and g are both defined in an interval I. So I is an interval on the number line, and t is the number line variable, so t is an I. So I is an interval for time, or t. So the equations x equals to f of t and y is equal to g of t are what we call parametric equations. There are 2 equations with parameter t. That's the name of the variable. That's the role it takes. T is a parameter. So it's just some third thing. Normally in physics we add a third variable, z of t. Right, so if I have some movement in the coordinate grid, the 3-dimensional coordinate space, then x, y, and z are all functions of time. They all change with respect to time. A lot of the times that's the way physicists think. Okay, so example number 1. So we're going to try to graph and make sense out of this thing. What's the curve that's generated when I plug this in? X is equal to t squared minus 1, y is equal to t minus 2. And we're going to do this for t is in this interval -3 to 3. So I'm literally only graphing for -3 seconds all the way up to 3 seconds if I want to think of it as a time variable, because t is time most of the time. So here's what we do. I'm going to make a table, and the table is going to have 3 columns now. So t, x, y, if that makes sense. Hopefully it does. So -3, and we're going to do this every one value up. So -2, -1, 0, 1, 2, 3. I'll make vertical separations for each of these, so that way we have rows now. Those don't look too bad, I guess. And then when t is equal to -3, what you're doing is you're plugging in t into both of those equations, t squared minus 1, and then t minus 2, which I'm tempted to go ahead and go to a calculator and plug that in myself and then just copying all of them. That's exactly what I'm going to do. So I'm going to stop here. And here's the information now. So what I did was I just plugged them into a calculator, typed it all in, and then copied in all of that information here. So that way we can just save a little bit of time. So there's that. So it's literally just plugging in the time variable value into this function, and again into this function to find either of those two x and y coordinates. So what we're going to do is we're going to play around with the idea of those types of equations and see what the graph looks like. So those are ordered pairs, an x coordinate and a y coordinate at time -3. So what I'm going to do is I'm going to disregard the t values now, and all I'm going to do is plot those points that we got. So how many points do we get? 7 points total, it looks like. So we're literally now only plotting 7 points, and they're going to be connected with a curve. So let's see, 8, -5. So 8, -5 is my initial point. That's my very first point. So I got to keep track of that. 8, -5 is my very first point. So there's going to be some movement, and what we're doing is we're generating a curve. Think of this as like a particle moving along this this coordinate grid. So then the next point that it moves to is 3, -4. So 3, -4 is here. So that moved this way. And I'm going to connect the dots maybe later once I see what the pattern looks like. 0, -3 is the next one. So it moved from here to here to there. Let's see. -1, -2, -1, -2. And you kind of see a pattern already. It's curved. 0, -1. Oh, and we no longer have a function, it looks like. This is a relation, and that's fine. So that's perfectly fine. Let's see, 0, and I think I did this wrong, didn't I? -1, -2. Oh, I see what I did wrong. I didn't type one of these. Oh, there we go. Okay. 0, -1. And look at that. That's no longer a function, which is fine. So if I take these ordered pairs and just plot them the way they come out, you're not always going to get a function. It's just going to be some general curve. And that's what ends up happening after we play around with these types of equations, which I might move this over to the calculator in just a little bit just to show what that curve ends up looking like. We keep on going. So after 0, -1, it's 3, 0. So now here. And then it's 8, 1. What type of curve does that look like? That looks like a parabola. So it started here. And all it says is list the ordered pairs. That's all it says. But the idea is I could have done this so that way the x-axis was done with even more points. So I'm going to go ahead and connect the dots, because if I connected the dots, it looks like it's going to be a parabola. It looks like this. But they only want it for t between -3 and 3. So it has to stop there, and it has to start here. So this was the start. T equals -3 here. T equals 3. This was t is equal to -2. T is equal to -1. T equals 0. T equals 1. T equals 2. So that's kind of cool. And that's the curve that we get. So what I'm going to go ahead and do is I'm going to go straight to a calculator just to show you what that looks like in a calculator, because you want to know how to do this in a calculator. So this would be for an Inspire calculator. And what I'm going to do is I'm going to add a graphs page. So on a graphs page, its default is for y as a function of x. So we're talking about the normal way that we do this, graphing functions. And we're not going to graph a function, I want to graph a parametric curve. So let's see, or a plane curve. So what we're going to do is press menu, and then we're going to change the graphing type. So it's going to be not a function, not a relation. Parametric number 4 is what I'd like to do. So this one, equation templates, these are for specific types of special ones that we're not going to go over. So parametric number 4, x of t, t squared, minus 1. Make sure to move outside of that square. Let's see, and then this was what? T, I forgot. Minus 2. I was looking at the notes. So t minus 2. And the step here, and then the interval. Interval from 0 to, they're going to 2 pi approximately. We want to do -3 to 3 is what they wanted. T step is for how many individual points in between. I'm going to do 0.1. So that's just because it's a computer, and it's going to do this and make a table. And what they mean is starting at 3, what's the next one up? It's going to be 0.1 up. So that way we can do a bunch of points. So I'm going to leave it that way. And that's what the curve looks like. So let me move this. So it's 2 equations, x and y. And that's what the curve looks like. So it's a quadratic. Looks like I did a decent job with the table. But then again, I'm supposed to do that decent of a job because I let the calculator find the table for me anyway. So, but that's what that looks like. Alright, so for example 2, this is a continuation of example 1. This is the next thing that you want to know how to do when it comes to parametric equations. So the next skill that you need to have learned by the time you finished pre-calculus is how to find a rectangular equation which eliminates the parameter t. So I want an equation that links x and y together. So if t squared is equal to x and y is equal to t minus 2, can I come up with an equation that eliminates t and links x and y to each other? The answer is yes. So here's how we do it. So first off, the one that has t in it is right here. So I want to solve for t and then do a replacement or a substitution, and that's how we're going to end up eliminating the t variable. That's the game plan. So look at that equation. I like that one. I don't like this one because there's a square on that, and I'm not going to square root both sides or anything like that. This one's much easier. And I'm going to go ahead and add 2 to both sides. You get y plus 2 is equal to t, and that's what I'm plugging in for t here. So x is equal to t squared minus 1, or y plus 2 quantity squared minus 1. And we expand that. That's a polynomial. We know how to expand those. That's a y squared plus 4y plus 4. And then that's minus 1. Which I could just subtract 1, no problem. Y squared plus 4y. And then plus 3 is equal to x. Yeah, that's equal to, oh, okay, so, yeah, that's what x is equal to. And that's the equation that's rectangular between x and y. So that's the thing. So we have x as a function of y, right? So we've completely eliminated t. And there's one more thing I'm going to want to do, is they gave me instructions for where t is going to live inside. Now, y is the independent variable. So what interval will y live inside? So if t starts at -3 and then it ends at t equals to 3, where does y start? And where does y end? So y starts at -3 minus 2, right? You plug it into this equation. Y is equal to t minus 2. So I'm going to plug in -3 into there, and that's -5. So y starts at -5. And that goes to y equals, and let's see, you plug in 3, you get 1. So it stops at 1. So what I'm doing here is I'm actually finding the range of this function, or the y domain, basically. That's a weird one. So y goes from -5 to 1. Is that consistent with what we drew out here? -5 to 1. And yeah, it is. The lowest y coordinate we get is -5. The largest y coordinate we get when t is equal to 3 is 1. So that's just tracking the y coordinate for both of those points. T is equal to -3, and I forgot the negative there. And then t is equal to 3. So the y coordinate spans linearly from -5 to 1, and that's how that works. But here's our equation. That's what they want. They want us to eliminate the t variable, and that's it for example 2. That's the other major skill. So then anything else after that is figuring out how to draw these curves. So we want a graph number 3, and that's all they want is the graph. between 0 and 2 pi. So there's a little bit of both that I'm going to try to combine. So what I'm going to do is I'm going to do what we did here for number 2, because that's going to help. I don't want to draw a table. Tables they're annoying. They're kind of boring and they're annoying. So if I can understand this way and maybe graph this, which maybe this is a little harder to understand. We've never studied parabolas like that yet. That's in chapter 9. So we'll see. So it's better to have plotted points, and it was easy to see after we plotted points and then looked at the calculator. This one, because there's cosines and sines in it, I think we can make sense out of it a little easier. So x is 4 cosine t, and y is 2 sine t. So for example 3, I might want to treat this like I did example number 1. And for example number 1, we made a table. So t, x, and y. And because we're going from 0 to 2 pi, those are radian values. If I can understand them that way, that might be a little easier. I'm going to do 0. How do we normally do this? If I were drawing sinusoids, we draw 5 points. 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? So let's do those. And that's only 5 points though, so I might want to zoom in more and maybe add more points. But if I need more points, we'll see what happens. Pi, 3 pi over 2, and then 2 pi. Should be good enough. So maybe that's going to be good enough for us to figure out the shape of the curve, and if not, I'll just go to the calculator for help. So we're talking about cosine, and if you remember the pattern for cosine, 1, 0, negative 1, 0, 1. So this is 4, 0, negative 4, 0, 4. You don't remember? Look back at chapter 6 and graphing sines and cosines. Remember the pattern for sine? Pattern for sine was 0, 1, 0, negative 1, 0. So this is 2, 0, negative 2, 0. No. Way off. I just completely contradicted myself. That is 0, 2, 0, negative 2, 0. Remember, sine starts at 0, and then you multiply everything by 2. Cosine starts at 1, and you multiply by, in this case, it's 4. I was still thinking cosine. So, how do I graph those? So when time is 0, or t is 0, we're graphing the point 4, 0, that's here. So that's t is equal 0. When t is pi over 2, we're graphing 0, 2. So that's t is equal pi over 2. And that's how I'm keeping track of which one's first, which one's second, and so on. Next, negative 4, 0. T equals pi. And there's going to be 2 more. 0, negative 2. That's when t equals 3 pi over 2. And then 4, 0. And that's back where I started. So this is also for 2 pi. So I might need some more points in between, but if I were to guess, that looks like an ellipse. So if I had graphed a few more points, maybe let's say pi over 4, square root of 2 over 2. So that would be 2 square root of 2. And this would be square root of 2 over 2 times 2 is square root of 2. And that's kind of weird. So x is 2 square root of 2. What does 2 square root of 2 look like? So 2 square root of 2 is like 2.8. And then square root of 2 is 1.4. Yeah, 1.4. So it's like 2.8, which is about a 3, and then 1.4 somewhere around here. So yeah, it's going to end up looking like an ellipse. So I'm not going to draw any more than that. It's an ellipse. And there's a way to recover the equations, but we haven't gone over conic sections yet, which I don't understand why they're going over this section before conic sections. And that's supposed to be an ellipse, so pretend that's an ellipse. So that's going to be example 3. So really just plot points and kind of follow the curve. At this point, you'd probably want to look at the calculator to see what that's going to end up looking like, and you can just follow what the calculator looks like. And I won't go to the calculator for this one. I'm just going to do example 4, and that's going to be it for today, or for this particular topic. So, give 2 parametric equations for the equation of the parabola. Give 2 parametric equations for the equation of the parabola. So in other words, give 2 rules, like they gave here, 2 equations that end up having the result. So Like we did here, we were given two rules. Find the rectangular equation. So we went from there to there. Now they're asking, go backwards. Go backwards. Can you come up with the scheme for separating x and y as functions of time or functions of t? And it looks like I can. Take this to be t. So you get y is equal to t squared minus 1. And x then, which is kind of weird. X minus 3 is equal to t. Solve for x. X is equal to t plus 3 then. Those are my equations. And that's it. So that's going to be it for example 4, and that's also where I'm choosing to stop, because anything else after this is not really going to be important. So it's just being able to think of those as separate equations, and those two equations generate a curve on the coordinate plane. And that's going to be it for this particular section. So we're going to stop here. And that's also the end of chapter 8. So you're going to be, if you're in dual enrollment, you're going to be tested over sections 1 all the way through 8. So there will be a review for that, and there's going to be a test for that. So be looking out for an announcement from me on Google Classroom for more information on that.